Hello, everyone, and welcome back. My name is Mr. Cobalt, and in this video, I'm going to continue to talk about the acid-base properties of ions and salts. So, from this video on, we're going to be talking about the cation ions as weak acids. In the previous couple videos, I talked about anions and how those act as weak bases. So now we're going to go into the cations. But before we get into that, there was something I forgot to talk about in my last video, and that is this right here. So when we talked about how we could use the Ka value from our acid, right, to find the Kb value of the conjugate base of the weak acid. And so we know that the Ka value times the Kb value is equal to the Kw, which is 1.0 times 10 to the negative 14. We could use that to plug in. We could plug in the Ka value of our given acid and find the Kb value of the conjugate base of the anion of that conjugate acid. So, but we also can do some mathematical manipulation here, just like we did with the pH and the pOH. And we know that the pH plus the pOH is equal to 14. Well, we can do the same sort of calculation here with Ka and Kb. So as you see here, if I take the log of both sides, if I take the log of Ka times Kb, and I take the log of Kw, which is the same as the log of 1.0 times 10 to the negative 14, and then I start to break this apart, right? So according to the law of logs here, if I am taking the log of two things multiplied, then I can separate those and add the logs separately. So here I have the log of Ka plus the log of Kb is equal to the log of Kw is equal to negative 14. Now, what I can then do here, and then there's a negative here that I put, but so negative 14, what I can do is I can take the negative and bring it over on the other side. So I can take the negative of both sides. So if I take the negative of that side there, if I divide this by negative 1 and I divide this by negative 1, or multiply by negative 1 both sides. So either way, if I multiply by negative 1 here and I multiply by negative 1 here, it gets me a negative, right? So now this side would be negative, and then this side would be positive. So now I have the negative log of these two is equal to the negative log of Kw, which is equal to 14. Okay, I distribute the negative, so now I have negative log of Ka's plus the negative log of Kb is equal to the negative log of Kw, which is 14. But we know that when you have the negative log of something, that's the p function, right? So the pKa, the pH, right? So the negative log of H is the pH. So we can then rewrite this as, since the negative log of Ka is the pKa, and the negative log of Kb is the pKb, those two added together is going to equal 14, which is the pKw, since negative log of Kw is pKw. So we have this relationship here that we can use as well. So I just wanted to go over that since I had forgotten to go over that in my last video. Okay, so now let's get into cations as weak acids. So here, the cations can act as weak acids just like the anions can act as weak bases. So either the cation is going to be neutral or it's going to be a weak acid. So we can divide the cations into three groups. So either the cation is a counter ion of a strong base. That would be like NaOH or MgOH, right? So magnesium hydroxide, sodium hydroxide. In those cases, the cation, sodium and sodium hydroxide, is going to be the counter ion of a strong base. In that case, it's going to be neutral. It's going to be pH neutral. So sodium as the counter ion of NaOH, which is a strong base, is not going to do anything in the water. It'll be hydrated by the water, it'll interact with the water, but it's not going to ionize the water and take a hydrogen from the water. Okay. The second group we have is that the cation acts as a conjugate acid of a weak base. So in that case, it's going to act as a weak acid. And so I have here an example. So in this case, the cation can be formed from a non-ionic weak base by adding H plus. And here are a couple examples. So I have NH3, which is a weak base. If I add H plus to that, I get NH4 plus, the ammonium ion. This will act as a weak acid. It's the cation of the weak base. Okay, so this is a conjugate acid of the weak base NH3. I can form the cation from this base. This is a weak base, C2H5NH2. I could add H plus to this, and I get C2H5NH3 plus. So this cation is the conjugate acid of this base. So both of these are going to be acting as weak acids. So remember, the conjugate acid of a weak base is also a weak acid. So when you put these in water, if I take my NH4 plus or if I take my C2H5NH3 plus, throw that in water, it will then interact with water by donating a proton. So these are now going to act as a Bronsted-Lowry acid. So here I have my BH plus aqueous plus water. The H plus is going to come off, add to the water, transfer to the water, give me my hydronium ion, and then I have the base left over. So what I can do is I can calculate the pH of this weak acid, just like of this conjugate acid of the weak base, just like I would calculate the pH of a weak acid. So again, what you would do is, so since this is the conjugate acid of the weak base, I can treat this like I would any weak acid, but because this is the conjugate acid of a weak base, I'm not readily given the Ka values for these conjugate acids. So just like before, I have to go to my base, and in this case, I'm going to have to look up the Kb, or it's giving me the Kb, and then use this equation. Ka times Kb gives me Kw. So in this case, I'm looking up the Kb's of these bases, plug in the Kb of the base. I know the Kw is 1.0 times 10 to the negative 14. So then I can solve for the Ka of my conjugate acid. And then once I know the Ka value, it's just an equilibrium problem, just like we normally would do for a weak acid. So I have my Ka value. I set up my ice table. I figure out, I'm given the initial concentrations of my conjugate acid. I do my ice table. I figure out what the equilibrium concentrations are in terms of X, plug that into my Kb expression for this equation, and then I can either use the X's small approximation to simplify the calculation and solve for X, or I could use the quadratic formula to solve for X, or I could use the method of successive approximations. Either way, I solve for X. X is going to be the H plus concentration. So once I find X, I know the H plus concentration. Therefore, now I can find the pH by taking the negative log of the H concentration. So just like a normal weak acid problem. Okay, well, what about the third category? The third category is that you have a small, highly charged metal, and those can act as acids. So those can be acidic in water. So these would be like metals like aluminum 3 plus or iron 3 plus, highly charged metals, and they're small. So how does this work? Well, if we take aluminum 3 plus as an example, what's going to happen is it gets hydrated by water, and it forms a hydrated complex around the aluminum. So what happens is you have this aluminum, you throw it in water, and then 6 water molecules will complex with and bind with the aluminum to form this complex here. So you have aluminum with 6 waters bonded to it, and then the whole thing has a 3 plus charge. Well, what does that look like? So I drew a picture here. So you have the aluminum with a hydrated complex. So here you have 6 water molecules that are bonded to the central aluminum, and it's the whole thing, the whole complex has a 3 plus charge. So why does this become acidic? Why does this lower the pH or raise the H plus concentration? Well, what happens is because this is a highly charged small molecule or atom, uh, this is going to make these water molecules more acidic. So basically the positive, highly positive charge is going to attract those electrons from the water. And so then the water molecules are going to hold on less tightly those hydrogens. And so then the hydrogen from one of the waters is going to add to a water molecule in solution. So let's say this water molecule here donates an H plus, right? Now this water molecule becomes a hydronium ion, and now the complex here now has an OH minus bonded to the aluminum. And notice that the charge becomes a 2 plus instead of a 3 plus. So it lost a positive H plus here. It's gained a negative OH minus. That's going to cancel out one of the charges and give you a 2 plus. So this allows this to become a 2 plus charge, and so now this is going to donate a hydrogen. So this becomes a Bronsted-Lowry acid, and this is our Bronsted-Lowry base. So that's how this can cause your solution to be acidic. So those are the 3 categories. So 1, you have counter ions as strong bases. Those are going to be neutral. Your cation could be the conjugate acid of a weak base, therefore it's going to be a weak acid. And then you have a highly small, highly charged metals. And so any highly charged metal is going to do this sort of thing here. So your group 1 metals and your group 2 metals are not going to be doing this very much. So you won't see this sort of thing happening with group 1 or group 2 metals, but you will see them with other metals that are small and highly charged. I hope this is helpful. If you enjoyed this video, if you got a lot out of it, please make sure you hit that like button right there, smash it. Also, subscribe to my channel. Hit that notification bell so you'll be notified by other videos I put out. Put a comment down below in the comment section. Let me know what you think and if you've got any questions for me. Thanks for joining me. Have a great day.